Hi, this is Shane Mueller for another chapter of the book, Chapter 7, Applied Statistical Analysis for Psychology and Human Factors and Data Science. So, the link that you can get all of the materials on will be in the download section in the summary. You can go here to get this, scroll down to, um, let's see, scroll down to Chapter 7, and there's a couple files you should download. Chapter 7 supplemental materials. If we look in here, this has all the figures that are created. Really, the only thing you need is this Chapter 7 walkthrough file. Although one of the examples asks you to download this and do something. I don't think we're going to cover that in the video, so you probably don't need that for the video, but you can work through that yourself if you want to know how it works. So, just a few thoughts before we begin. We're now past the first section of the book, the first sort of unit, which is about reading data and managing data, graphing data, and displaying, visualizing data. And this is sort of unique, I think, for a statistics course where the first time we talk about things like probability theory are a third of the way through the class. And this is really by design. Um, the design here is that we want to be able to handle data, be comfortable doing things with data before we start thinking about probability theory, so that when we start doing statistical tests, you are comfortable um, managing data, you're comfortable with things like looping and aggregation and applying functions to data. And so that's sort of the motivation here. and and so this is the first time we really talk about things like probability theory. So the the basic idea for what I'm going to do today is talk through a lot of the examples in Chapter 7. Now, especially at the beginning of Chapter 7, there's a lot more reading to be done that I'm not going to cover in detail. And and this should be a review if you've taken other stats courses before, but it's good to have a reminder. So I'm going to talk a little bit about things from the book and then focus on examples that we can use. And so you should download that material. I have loaded it into our studio here, and I will always remember to set your working directory to the source file so that you, if you load something in or save it, you have the right location. All right, so to begin with, this is the first time we talk about how we model the world with statistical models. And if the world, if we knew everything about the world or everything about a system, there would be probably no need for a statistical model. We could just do a physical model, and we'd be able to predict 100% with 100% accuracy what's going to happen. But what we have this notion that we call randomness, and really the notion of randomness is one of unknown factors. There's unknown processes, unknown information, unknown forces, um, unknown unknown aspects of anything that happens, meaning that you don't know it, and so you can't predict 100% of the time the outcome. So that's really all I think we mean as randomness. It's not like necessarily a property of the universe. It's a property of our understanding of the universe. So when we don't know something, we can't predict it. And so if we make, or to the extent we can predict it, there's going to be variability. And that variability and sort of the unknown information we just refer to as randomness. Um, when we're trying to understand something in the universe, in the world, maybe the behavior of a person, maybe whether someone is going to visit a website, or whether someone who visits sees an ad on the website will be converted to a buyer. Um, these are sort of very concrete behaviors and events. But in aggregate, we like to think of these, we like to understand these at a statistical mathematical level. And so we build a model of that. And so the process of doing statistics at its core is building a model of the process we're interested in. And for the most part, this is building a model of human behavior um, of some sort or another, human behavior or human effects of something. So we do this, the model of the universe, we describe in statistics as a random variable. So the concept of a random variable is pretty simple. It's a function that can represent the randomness of outcomes. And we'll talk a little bit about defining that. So what is a random variable? Well, first it needs to be defined based on a sample space. A random variable, the sample space of a random variable are just all the possible outcomes. And so the standard examples, if you have a coin, it's going to be heads or tails. If you have a die roll, it's going to be 1 through 6. And so there's two types of sample spaces. One are discrete, and that would be like heads or tails, 1 through 6 on a die. And one's continuous, and these are real numbers, so like the age of a person, at least within a range. So a person is not exactly 20 years old, but you can sort of say anybody who's in their 20th year is called 20, and so I guess you could consider that a discrete, but if you think about it as in terms of the time since they were born, this would be a continuous variable. These differ a little bit in how we deal with them, and so that's why it's important to make this distinction. And so the sample space is just the possible values it takes, and what a random variable does is it tries to assign values, which we call probability measures, to all possible subsets. All that means is any possible kind of type of event you could describe using words like and or, you can assign a probability measure to. You can assign a number to. So the method, the mathematics by which that number is assigned, that's called the distribution, or specific aspects of that are called the distribution of the random variable. Now, the interesting thing is, like to say, well, we want to assign numbers to the subsets of the sample space. This is kind of abstract, and so what mathematicians have done is they say, well, let's come up with some assumptions that help guide how this works. We'll make a limited set of assumptions, and based on those assumptions, we'll build a whole system and know how this works. And so these are called axioms. So the axioms of probability theory are really quite simple. And it's all based on this notion of a sample space and subsets of the sample space. So you could think of subsets of a sample space sort of like the things you could bet on in roulette. So if you see a big roulette wheel, or you see the table you can bet on roulette, you can say, well, I want to bet on black, or I want to bet on red. This would be one subspace of all the possible things it could land on. Or you could say, I want to bet on number 27, and that's another subspace. It's or you could say, I want to bet on odd, or you could, and then there's ways you can bet on like 4 numbers, 1, 3, 5, and 7 or something. Or you could individually place money on everything on the table, like every single number. So you're guaranteed to win, or all but one thing. So these are all possible subsets of that sample space. And what probability theory does is just it tries to assign measures to each of those. And if you can define a mathematical formalism where you can make a consistent way of measuring the probability of any type of subset, then that's a random variable, or that's a distribution of the random variable, and we have a consistent probability theory to base a model of the world on. So the assumptions we use to do this are three. First, the assumption is that the empty subset is zero. So this is almost just like a technical definition. If if you have no things that you're trying to measure, it's zero. So that's the baseline. The baseline zero. And if you have the entire set, so if I want to characterize one of any of the numbers in roulette will come up, and you add the measures all up, that has to equal one. So these sort of bound you at the bottom and at the top. And then the only other axiom is a little more complicated, but not much. It says the probability of the union of several mutually exclusive subsets is the sum of the probabilities of the subset. And this is where all the action is. So if you have this measure that says probability is of some set is something, and you add to it another subset. So if I take odd numbers and then I add, and maybe the probability of that on a roulette wheel is close to 50% or close to 0.5, and I add to it one even number, so that's like 1 over 37 depending on the wheel, then the probability of these things together, because they're mutually exclusive, is the sum of the probabilities of each individual. So it's going to be 0.5 plus 1 over 37 or something like that. So that's the only real rule about what we mean by probability, and all the rest of probability theory is based on these assumptions. And curiously, these are not like proven. These are just taken as given, and we build the system based on it. And people have explored alternatives to these three axioms as well. Sort of. So everything is based on these three things. So when we talk about a random variable, then we can define some rules, some mathematical formulas that obeys these properties that describe the distribution of that random variable, or how probabilities are assigned to the sample space, and thus in the random variable what type of things are more or less likely to come up by chance. Here's some examples of random variables, and I think I have the code in here in the walkthrough for generating these, and it's pretty straightforward. When you have a discrete random variable, we often represent these as like a bar plot. And so you might have, for a coin toss, the probability of heads is 0.5 and the probability of tails is 0.5. Or for a die roll, the probability of each of these is 1/6. And for a continuous random variable, like the normal distribution, you don't have probability mass, which is what this is called. It's labeled probability density, but this is really typically correctly referred to as probability mass function. You have a probability density function. This is because if you think about it, like if you if you know what like a continuous line is or continuous real number is, if you pick any particular value here, the chances of this random variable taking on that value is zero. It goes to zero, because there's an infinite number of possible values it could take on. But that doesn't mean everyone is equally likely. You can have, even though for any particular value at zero, you can have some areas more likely than others. For a continuous value, you can only measure probability by ranges of this. So I can't say the probability, well, I can say the probability of it coming up zero is the most likely area, but it's actually zero. The probability is zero. But the probability of it coming up between zero and positive infinity is 1/2. So I can take the measure of ranges of this, which is going to be the area under this curve. But the height does not represent a probability. It represents what's called the likelihood, or a probability density. So some areas are more likely than others. This is why for a lot of continuous random variables, we like to look at the cumulative distribution function, which you see here, which, if you remember calculus is going to be the integral of this. And so any value here is going to tell you the area to the left of that. So here, if we look at 0, the area to the left of 0 will be 0.5. And so that tells me, oh, the area under here to the left of 0 is 0.5. And the area maybe to the left of 2 is, say, 0.98. And so now I can use this to measure the area under any 2 points just by subtraction. I can say 2 minus 0, well, that's going to be by about 0.48. So these are some of the ways we describe the density, the probability density, the probability mass function, and the distribution function of a random variable. So the distribution is a property of the random variable, and it's just the way in which the random variable obeys these laws and assigns probabilities to subsets of the sample space. Okay, so in the book, I describe a number of random variables and how they might be implemented or simulated with R. So, for example, here is flipping a coin. And so this simple example, let's see, says, let me flip a coin and see, I'll give it a certain number of flips, and the coin will maybe be biased or unbiased, and I'll give it a number of repetitions. And so if you walk through the logic here, it's nothing we haven't done in previous chapters, or here's a function that will flip coins for you. And I'm going to, this runs it like 100,000 times, so it's not too, it doesn't take too long, but sometimes 100,000 doesn't seem like enough. You might want to run it a couple million times, and it might take longer, so I just have it guarded by this if it exists, so that we can not run it if you already done it. And so what happens when you flip like a coin 10 times, that's fair. What happens if you flip a coin 10 times that's slightly biased, is what we're asking. And that's what I'll plot first. And this sort of, if you're familiar with a normal distribution, sort of looks like a normal distribution. It isn't. First of all, it's discrete. So if you flip the coin 10 times, it can't come up 9.5 times. It can only come up 10, 9, 8, 7, 6, 5, 4. It has to be symmetric around 0.5. And that shows it, it's biased, that it's unbiased. But recognize that this is the result of running this experiment of 10 coin flips 100,000 times. These are the numbers I got across those 100,000 times. I would never observe this whole thing in a single experiment. I would only observe 1 point, 6, 4, 5, 2, 1, 0. And so if you're trying to figure out if the coin is biased, you would never know by doing one experiment, or you may never know. Let's look at what happens when we have a biased coin. Here's what fair would be. Here's a slightly biased coin, and you can see for 10 coin flips, they're not too different. And even something like 8, which seems like, well, this might be strong evidence for bias, it's only slightly more likely for the biased coin than the unbiased coin. Maybe it's 50% more likely. And as you get out to the edge, both of them are really rare, so you can't, you'd be hard pressed even if you saw 10 to say, well, this is a biased coin. It doesn't happen too often with either the biased coin you saw or a fair coin. So now what if I, instead of doing an experiment with just 10 coin flips, I did it with 1,000. Now I get a distribution like this for fair. You can see it's going to be centered at 250, but even with the same bias of 55%, now the distribution is much different. So for 250, if I see about 263 or something, then it's equally likely, you see these cross here, that's sort of the equally likelihood point. It's equally likely to be this fair coin or this biased coin. I guess this would represent a case where I tell you, in one hand I've got a fair coin, in one hand I have got a biased coin that lands on heads 55% of the time. Can you tell which one it is? Well, you could make a guess. If it was 250 exactly, um, it's much more likely to be the fair coin than the biased. And if it's 280, it's much more likely to be the biased than the fair. And if it's 300, that's almost impossible with the fair coin, but it's sort of likely with this biased coin. So just by doing larger experiments, we can make better distinctions between whether this is fair or not. And that's sort of the big picture of you know what of how we use probability to make inferences about the world. Okay, so in the book, I describe a number of possible distributions that you could use and how we can implement them in R. And so here's discrete, both uniform and non-uniform. Here's continuous. A continuous random variable could have a min and a max, or it could this is sort of what it looks like in a histogram or in a scatter plot. The distribution for coin flipping, the number of coins that reach heads out of n is binomial, and here's another example of binomial of an unbiased and a biased coin. And here this would be out of 15 coin flips, if the biased for heads is 0.4 versus 0.8, this is what the distributions look like. And next we have the normal distribution, which is sort of really one of the most popular, commonly used distributions out there for a number of reasons. And we can generate random versions of this using the rnorm function. And if I generate that and I do a histogram, here's one sort of sample from 1,000 draws from a normal distribution, and that's what it looks like in a histogram with bins this size. It's sort of jaggedy. It's not going to be extremely smooth. We only have 50 in each bin, so sometimes it goes 50, sometimes 40. And then down here we only have 10 or 5, so we see sort of fuzziness around the shape of this distribution. There's a number of functions within R that let you estimate quantiles and things, but as I set up earlier, the curious thing about this distribution, which is the most commonly used distribution for statistical inference, is that although we do know the shape, we have a way of writing down the shape of this function. The mathematics for the shape of the bell curve are known. That's usually not the most useful thing for continuous variables like this. We want to know the cumulative, and the cumulative, unfortunately, is not known. There's no way of writing down a form of that cumulative function, and so we rely on numerical estimates, which are pretty good, but all of this is actually generated from not a numerical estimate of the normal distribution, not the actual normal distribution. All right, so now that we've talked about different distributions, we can think of, and different random variables, we can think of how to generate and view samples from them. And that's really the approach we'll tend to take in this class, or in this book, is rather than making a proof of convergence or calculating the integral of the area underneath some random variable, we will look at these through simulation, through Monte Carlo simulation. So we'll run a bunch of samples from these things and look at their properties visually or through other means. So here's a few exercises that you should be able to do. Okay, so we talked about the normal distribution before, and some of its properties that people rely on or use and sometimes ignore when they model some process are, first of, it's continuous. So you have to recognize that any rational number could be observed, and this is almost never the case for anything we really measure. Things we measure are usually not really continuous. They are discretized at some level. Even if it's an electron microscope, there's a certain number of microns it can only measure. Um, Next is its sample space or range is infinite. There's no minimum or maximum value. And so if you have something like a test score that you're measuring, you're violating one of the assumptions because you can't get a negative test score. Practically, you're violating it, and you can't get them over the maximum of the test. But people still, will. Um, so a test score is also not continuous. So a test score will violate both of these, but people still will use it to use the normal to model that. Another fact is that it's symmetric, um, and a lot of our data are not symmetric, but we may still use a normal distribution to model them. It has what I'll call the Gaussian shape. It has a specific shape, and the specific shape of the normal is different than. It's not just symmetric, but it has a very specific properties. There are other distributions that are not too different from it, like the logistic. Logistic is slightly different, has a slightly different shape. It's usually not detectably different. Um, and it's also commonly used for some statistical models. Um, Also, this is a big one that we assume that the data that we're observing came from an unchanging process. It's sort of it's called stationarity. That all the data that you're modeling were sort of independent draws from this distribution. That's hardly ever the case, but we often make that assumption because we wouldn't be able to make any progress if we didn't. But if you have data, you can try to evaluate all of these things, either logically or with histograms and things like that to determine whether you have any strong violations. But so you can do it sort of ad hoc. One of the best ways to look at a distribution and see if it violates the assumptions of the normal distribution or whatever distribution you're looking at is through something called a QQ plot. And a QQ plot is short for quantile plot, and it's basically a way of comparing the shape of two distributions. And so you plot the quantiles of one distribution against the quantiles of the other, and look at the result. And if they have the same shape, you should see a straight line. The normal QQ plot then plots your data against the quantiles of a normal distribution. And so here I'm making sort of a QQ plot by hand. If you've got, so it's sort of tricky if you have data from different numbers of samples, because then you have to make sure all of the points you have in your data have an equal number of points in the distribution you're comparing it to. But here are what I'll do is I'm sampling from a normal and a uniform, and then comparing it with a QQ plot to the hypothetical quantiles of the normal and the uniform for each one of these. And you see I just sort these. This puts them in order of quantiles. Since there's 100, it puts them in order of the 0 to 100th quantile, or the 0 to 99th quantile. And then I compare it to the 0 to 99th quantile of a particular distribution using Q norm or Q unif. So this plots it, and you can see that when you map a normal against a normal, you see a straight line. When you map a uniform against a uniform, you see a straight line. But when you map a normal against uniform or uniform against normal, you see this sort of S curve. And to the extent that you see an S curve or some other relationship, that's evidence that you don't have a normal distribution and you're violating some assumptions about the shape of that distribution. So when we're selecting our model of the world and we're basing it on, say, a normal distribution, we want to verify that we're correct. We want to verify that it's a reasonable model, and a QQ plot would sort of be the minimum thing to look at. You could also look at the histogram, which might show you the same thing, but this might be a little easier. And this is really important, especially if you are trying to do statistical inference, like doing a hypothesis test, because the details of your hypothesis test will depend on your assumption, and your assumption is that it's normal. And so if it's not normal, your conclusions may be incorrect. All right, I have decided to cut this video into two pieces, and so this will be it for the first video, which focused on probability theory and random variables and distributions. And so just to summarize, we got through section 7.3 of the chapter. You should understand in general what a random variable is, some of the different random variables that we have available for modeling data, and a little bit of a sense for how you might be able to distinguish parameters from random variables based on data you observe. And so we did a few little experiments where we sampled repeatedly from random variables to see how differently they look when parameters differ. We also talked about the Gaussian random variable, and ways you can either simulate from it or look at numerically estimate the quantiles of it. And comparing then also methods for using QQ plots and Q to Q normal plots to compare your data to a given distribution, or compare two data distributions against one another to see if they have the same distribution. So that's a summary of sort of the first half of chapter 7. Next, we're going to look at using these models that we have of data to make inference about to make inferences about what the world is like based on a sample. That's the process of doing inferential statistics, and it's the process of observing a small part of the world and trying to make inference about what the bigger picture of the world looks like.